Jai Hind all. Myself Dr. Amita Asthana from Akgec Engineering College, Ghaziabad. So here we will study the Zener diode from Unit 1 of BEC 201, Fundamentals of Electronics Engineering. So here first of all we will understand what is a Zener diode. So the Zener diode is a kind of diode, okay, and it is very special type of diode which is allowing current to flow backwards when a set reverse voltage is applied, right? That means, let's say I'm taking a Zener diode. First of all, I will draw the symbol of the Zener diode. This is the P terminal of the diode and this is the N terminal of the diode. So when I apply voltage to this particular diode, let's say I am applying here a voltage of V, some V. Okay, this voltage, if it is connected like this, positive this side, negative this side, then this positive voltage will make this Zener diode in a forward bias condition, as we all know. And if it is forward bias, the Zener diode will behave in a normal manner, just like a junction diode behaves. But if I, let's say, what I do, if I connect this in negative, like in a reverse bias condition, V, okay, then the Zener diode is reverse biased in this case, and this, because this negative is connected to the positive P terminal of the Zener diode. So here the Zener diode will see if its cutoff voltage is Vz, let's say, then it will see what is the value of this. Let's say it is 10 volt and we are applying this V as 9 volt. Okay, it will behave normally. It won't react at that particular time when this 9 volt is less than its Vz. Okay, here in this case, then if let's say I apply a Zener diode of 15 volts here, this negative voltage has been given 15 volt. Now this 15 volt is greater than 10 volts, right? Greater than Vz. Then what Zener diode will do, it will work as a voltage source of value Vz, right? So it is allowing the current in a reverse type of thing. Okay, that means what it means, then Zener diode in forward bias condition behave in a normal manner, just like PN junction diode does, whether when the reverse voltage across the Zener diode exceeds its Vz, then it becomes a battery of Vz with the reverse polarity. That is the main point which we should remember. So some Zener diodes have a sharp, highly doped PN junction with a low Zener voltage. In this case, the reverse conduction occurs due to electron quantum tunneling. So the phenomena here is electron quantum tunneling. Okay, so this is known as the Zener effect. So this electron quantum tunneling is known as the Zener effect, which gives Zener diode being a sharp and highly doped PN junction. Now, diodes with a higher Zener voltage have more gradual junction. Their mode of operation also involves avalanche breakdown. It's not necessary that Zener diode will have only, the Zener breakdown. It may have avalanche also if the Zener voltage have a more gradual junction. Now, both breakdown types are present in the Zener diodes, with the Zener effect predominating at lower voltages, and avalanche breakdown requires some high voltages. Okay. In short, Zener diodes are optimized for operation in the breakdown region. Since Zener diode makes itself a negative battery when it is reverse biased, so we utilize Zener diode in its reverse mode only, right? Here we can see the characteristics graph of the Zener diode. What here we are going to see that when this particular region is positive voltage, this is I axis and this is V. So this particular quadrant is the positive voltage and positive I quadrant, right? So your Zener diode is behaving just same as your PN junction diode, but this in this region you can say this is a reverse bias. The third quadrant region is the reverse biased region, and after VZ the Zener diode is turning into the battery of VZ with the reverse polarity. That is the main point which we need to understand. For the forward biasing, the Zener diode is just behaving in the just behaving as a normal junction diode, and in the reverse bias condition, if the reverse voltage goes beyond that VZ, goes beyond the Zener voltage, then it becomes a battery of VZ with reverse polarity, right? So with reverse polarity means, if you can see here, this P, this is the P side and this is the N side. So this P will be negative and this N will be positive. That means what I am doing, if the reverse voltage is exceeding, if the voltage across the diode is exceeding VZ, then it breaks down into the battery of VZ minus plus, and here it is P and here it is N, right? This is how the Zener diode works, and this particular work is utilized as voltage regulator functioning of the Zener diodes. So this is a particular circuit which we use for the basic Zener regulator, and the numericals are based on this particular circuit. This is a proper Zener diode circuit which we are using. So here we can see this is a particular, we have input voltage source Vi, this is one resistance R, and here this is the load resistance, and this is the Zener diode whose Zener voltage is Vz. Suppose this input voltage gives a current of IR, okay, and here this is Iz. We can say this IL is the current through this RL. So these are some notations which we are using for solving these particular circuits. So here we can apply the Kirchhoff voltage law and Kirchhoff current law to solve the complete circuit. So here we are having three cases for Zener diode analysis. Three cases means the circuit would be the same, only the variations will be in the input voltage Vi and the load resistance RL. Okay. In first case, we have Vi to be fixed and RL to be fixed. The first case is Vi fixed and RL fixed, right? Now, second case would be, we will be varying the RL, and RL being variable component, and the Vi input voltage will be varying. In the third case, the opposite of the second case, Vi will be variable and RL is fixed, right? Vi being variable and RL being fixed. So we will analyze these circuits in three cases. Here in this video lecture, we will discuss the case 1 when Vi and RL both are fixed. This is a particular very simple kind of question that can come for this particular case, and this is very easy to analyze. So once Vi and RL is fixed, everything in this particular circuit is fixed, and Zener diode will stay according to the voltage across its terminal. So Zener will behave, it is going to behave in accordance with the input voltage across its terminals, right? So this is a particular circuit which we are going to see. First of all, the analysis can fundamentally be broken down into basically two steps. First of all, we will determine the state of the Zener diode. As I said, the Zener diode will behave same as the voltage is applied between its terminal. If the Zener diode find itself in the condition that the voltage across its terminal is less than Vz, then it is not it is not concerned actually. It is just like that, it is not present in the circuit also. You just catch my point, that I am saying if Zener diode is finding itself in the state that its voltage across the terminals is less than the Vz, then it will not react at all. If Zener diode finds the voltage across its terminals greater than its Vz, then it will behave and it will be very, very active, and it will become a battery of Vz. As I told you, in the reverse bias, either it is staying calm. Okay, if the reverse voltage is exceeding Vz, it is not in the very calm and cool condition. It will just switch itself, and it will convert in the battery of Vz with reverse polarity, as I explained. This is the key point which we need to understand. And then when we find out whether the Zener diode is working condition or Zener diode is not in the working condition, then rest of things becomes very, very easy. So first step is to determine the state of the Zener diode. Okay. So for getting the state of the Zener diode, we will calculate voltage across this particular diode. Okay. If here, if we apply the voltage divider rule, we will find that voltage between these two terminals is equal to the voltage across this two terminals. And if I say this voltage is VL and this is VI, I want to calculate by applying KVL. I will get VL is equal to RL VI R plus RL. This I can find out in applying Kirchhoff voltage law to the outer loop. You can derive on yourself. Okay. If V is greater than Vz, okay. If let's say VL is greater than Vz or V is greater than Vz, then Zener diode is on. Zener diode is on. That means it has been converted into the battery of Vz with reverse polarity, right? And if V is less than Vz, suppose this value comes out to be less than Vz, VL comes out less than Vz, then Zener diode is not active at all. Zener diode is not active. It is just, you can think of the diode that it is sleeping in the circuit. It is not active at all. It will act, react. It is on when the case when V or VL is greater than or equal to Vz, right? If this particular point is clear, then we can immediately convert this in the battery of Vz now and apply this. All the parameters are here. just you need to apply the Kirchhoff current law and Kirchhoff voltage law. If I want to apply Kirchhoff current law at this particular point, then incoming current IR is equal to IZ plus IL. So IR is equal to IZ plus IL, and now you can also apply Kirchhoff voltage law here, or you can also apply Kirchhoff voltage law in the first loop also. So KVL you can apply here, plus VI in the first loop, yes, applying this KVL, and minus IR into R minus VZ is equal to 0. One equation will be written like this. Now, when we come, and this is the Kirchhoff current law and this is the Kirchhoff voltage law, these two equations, when whatever the parameter has been asked, you just need to apply only the Kirchhoff current law and Kirchhoff voltage law. That means here the question becomes very easy. After finding out the state of the diode, now we need to convert the Zener diode into the battery with opposite polarity, and then we can apply Kirchhoff voltage law and Kirchhoff current law. One more thing here I would like to mention, that the power dissipated by the Zener diode is determined by PZ is equal to VZ into IZ. As IZ is the current through the Zener diode and VZ is the voltage across the Zener diode, so IZ into VZ is equal to power dissipated by the Zener diode. That's clear. I think P is equal to VI formula we have applied, nothing else we are applying, right? So here for this particular example, let us, the question is asking to find out for the Zener diode, determine VL, VR, IZ, PZ, repeat part with RL is equal to 3. So first of all, as I said, we are very eager to find out the state of the diode. In this particular circuit, I will apply the first formula. VL is equal to VI into RL upon R plus R. So VI is what? 16. RL is what? 1200 ohm. I have converted it in ohms upon 1000 plus 1200. Now 16 into 12 upon 10 plus 12, that is 22. So if I solve this, right, then I can multiply it and I can solve it. This value will come out to be 8.73. This 8.73 is less than 10 volts VZ. Okay, this is less than 10 volts. So Zener diode is how? It is just like that. It is not present in the circuit. It is not present in the circuit, right? If it is not present in the circuit, then circuit will remain same and you can leave the numerical at this particular point. Now, when RL is 3 kilo ohm, then this again we will find out for the second case we are doing. First case is over now. So 12 volt. Now this is greater than 10 volts, the VZ. So we will convert this Zener diode in the form of battery, and now we can apply Kirchhoff voltage law and this Kirchhoff KCL and KVL and calculate all these values IR and IL and apply this particular, and then after that you can calculate PZ is equal to VZ and into YZ. So look at the solution and then you can find out on your own. In the next video lecture we will discuss case 2 and case 3. Thank you.